On today's episode, we are joined by Konstantinos Karagiannis to discuss all things the quantum threat and why you should be paying attention, whether you are an organization, institution, or on an individual level. So, without further ado, let's dive into today's episode. Hey everyone, and welcome back to another episode of the QRL Show, the place where you come for the crypto and stay for the quantum. On today's episode, myself and Michael Strike from the QRL team are joined by Konstantinos Karagiannis, and he is the Director of Quantum Computing Services at Protiviti, spoken at dozens of technical conferences over the years, from DEF CON to Black Hat Europe, RSA, ISF World Congress, Security Congress. He has a lot of experience from the financial services industry, holding roles from CTO to, prior to that, global technical lead, ethical hacking, and biz dev. And Konstantinos is the host of the Post Quantum World podcast, where he regularly speaks with quantum computing experts on the latest and greatest in quantum computing, and really importantly, how that has a business impact and the benefits and the threats there. So before I jump into anything in today's conversation, Konstantinos, can you fill any holes in for the viewers of a quick minute or two background for anything that I missed there, and then we'll lead into the combo.
Oh yeah, that was a pretty intense intro there. Yeah, I just want to say, so it's been over a decade really heavily involved with quantum, and it's fascinating how when I first got into it, it was just security, security, security. Everyone was worried about the potential threat and crack encryption and all that, even though we were so far away 10, 11 years
Yeah,
ago.
yeah,
But yeah, in more recent years, it's shifted to also include these use cases, which is just really exciting stuff. Like right now, we can do pretty neat things with these machines that are helping companies. And this will be the case for a long time before we're all worried about, the apocalypse, really. So,
So it's kind
yeah.
of like this big solution looking for problems, right?
yeah, exactly. And we can't even think we've scratched the surface yet. Like think of the internet in the 90s. People thought it would be like a glorified billboard, maybe with like the ability to make an order for something or a little bit of shopping. If you read some of the earliest papers back then, no one would have envisioned this app culture with mobile and things obviously like the AI interactions we've seen in the last year. So we don't know, right? We don't know how many use cases are going to pop up, but so far we've nailed it down to like three general categories, which is just optimization, machine learning, and some type of simulation. You could pretty much think of everything falling under those three pillars, basically.
Yeah, no, that's perfect. And as a starting point to that, I think a good first question that will kind of unpack a number of other areas that we'll jump into is, maybe we could start out. We're going to keep, for those watching, we're going to keep a lot of this conversation about the quantum threat. So I think maybe a good first question would be, could you help paint myself, Michael, the audience, whether it's people at large organizations, companies, or on an individual level, help paint us a roadmap, so to speak, of the quantum threat? I know this is very broad and can cover a lot, but kind of help us give a little bit of understanding of maybe kind of what's been going on the past few years, and just give us some insight there, and then we can kind of lead into some different areas that offshoot from there.
Sure. So the quantum threat, it originated with this idea of Shor's algorithm in 1994. And there's been other impacts from that original work too, and also Grover's algorithm I'll have to mention in a moment. So the basic idea is RSA, public key infrastructure in general. That type of encryption relies on factoring, not being able to factor large numbers. So think about it. It's really, really difficult. 3 times 5 is 15. Sure, we can all figure that out. But if the number has 400 digits in it, good luck. You're never going to be able to figure out which 200-digit numbers made that. It could take forever. Um, so Shor's algorithm relies on periodicity of numbers and some other principles from physics to be able to determine two spikes, basically, that indicate which numbers were used to make that larger number. So that will drastically impact the security of RSA and the way that we send data in motion. Now, when you're talking about data that's stored, there's also a quantum threat, although it's a little different. So anything that's like a lockbox setup, data at rest. Think about like databases, or if you store your stuff deep on the cloud, just sitting there. That uses a key, and it'll use something like AES. So the only way to attack that would be with some kind of brute force approach. And if you use Grover's algorithm, it's a search algorithm. So whenever you do a typical search, it's n divided by 2. So if you're looking for something in a database of 100 items, you'll try about 50 times on average before you find it. With Grover's algorithm, it's a square root of n. So it would only take you about 10 tries. So you can imagine how that extrapolates when you're looking in really, really big key spaces. So even though quantum won't crack something like that, it will actually significantly weaken it. So if you have AES 256, for all intents and purposes, with a quantum computer of sufficient power, it will behave more like AES 128. So I wouldn't really call that secure. So those are like the two basic high level impacts that quantum has. Of course, as you guys know, blockchain also relies on a version of public key. And as a result, there's a way to find the numbers involved in ECC that are generating this key data. And it turns out that you actually need fewer qubits or quantum bits to reverse that. So there's some papers going around. I can give you links if you want to put in show notes. But the basic theories are that when it comes to weakening something like AES, you need around 6,000 error-corrected qubits. Pretty high number. When you want to weaken RSA, you need 2n plus 2 for Toffoli-based approach. So that would be for RSA 2048, you'd need 4,098 qubits, 2n plus 2. And then unfortunately for blockchain, you only need about 2,500. So that's quite a significant drop off. So that's where that initial threat appears. Now, there's plenty of roadmap stuff I'm sure we're going to dig into, getting to those error-corrected qubits, and then some other time modifiers. So I have a lot to say about that. I'll just pause for a second.
I think that would be good to get into. One question I kind of want to ask, and we can wrap up with this as well, or touch on this a little bit later in our conversation. I think one important part for those that are watching that are quite technical, they might have much stronger understanding on that than others. There's obviously a wide spectrum, but I'd love to cover maybe based on your being at the intersection, based on your experience, whether it's in financial services and then the overlap with quantum. What types of conversations are you having with individuals, whether it's heads of large institutions, large companies, down to the individual level, in terms of first unpack it or covering the why should they even care to take notice now, and then following that why, what can they do to proactively take some first steps in the right direction? Because obviously big corporations, big companies, they're steering very big ships. It's not like they can just turn on a dime. And so if you want to unpack that there, I know there's a number of layers to that, but
sure,
maybe give us a little bit insight, at least maybe on the conversations you're having and how maybe they're thinking about it.
Yeah. So before we deal with the actual timelines involved in hardware, there's a more looming deadline that no one's really considering. So I can share with your listeners right now, I know roughly within 12 months the exact date of the quantum apocalypse. Most people won't make that claim. I can make it. You know when it is? It's next year. And I'll tell you why it's next year. It's next year because next year NIST is going to publish its finalists for the ciphers that will be replacing RSA going forward. And what do you think is going to happen when NIST publishes those ciphers? Every regulatory body, every boardroom is going to be knocking on CISO's door saying, what are we doing about this? So the real apocalypse is really a year away. So that's the first big point I try to emphasize with customers I talk to. It's not about waiting 8 to 10 years for the first machines that might be powerful enough. It's realizing that once the regulatory bodies say jump, you have to say how high and by what day do you need me to do this jumping. And we don't even have to really speculate what these regulatory bodies are going to say, because the White House last May 2022, published a memorandum that very clearly details what we can expect federal agencies to have to do once the NIST finalists are published. So I don't think regulatory bodies are going to want to reinvent the wheel here. I think you can go and read that, replace federal for your, your line of business.
Fill in the blank.
Yeah, and you can expect that you're going to see those same targets. By 90 days, do this. By 1 year, do that.
And a lot
that's
of other
all going to
people
be
follow suit there. Yeah.
Yes, they're all going to cut and paste, really. I mean, I'm not accusing any regulatory bodies of plagiarism here. It's more like they're just going to take it as a best practice and they're going to run with it. We've seen this kind of thing before, and we're going to see it going forward. So that's like the first big thing that I point out to everyone. So we really don't have time. Like if you go to a conference and you listen to a cryptographer on stage, they're like, "Oh, it's 30 years away." They've been saying 30 years away for forever, and we'll get into why they're not even close on that one. But so that puts this sense of calm in people's minds, but it's not true. Once the regulatory bodies step in, that's going to be a doomsday of its own. So that's the one big thing. The other thing I like to mention, I've been mentioning for a while, is this idea of Moscow's theorem, and it basically states that you have to consider some other dates involved in this migration. One, how many years does it take your organization, like you said, steering a ship? How many years does it take to really make any kind of change in your organization? It's not overnight. Rolling out cryptography to your organization, key management, all that stuff. Yeah, that's not a 1 week project. You're talking years sometimes. So let's say it's 2 years, right? You got that number. Then you add that to the number of years you need any particular secret to remain secret, whether it's because of a regulatory requirement or the nature of the data. For example, Coca-Cola's secret formula, that's forever. Healthcare data, the lifetime of healthcare data is a lifetime. Like these last a long time. So you take those two numbers, you add them together, you're going to end up with something like 15, 20, 70 years. And then you say, okay, are we going to have a quantum computer that can crack encryption within that time period? And the answer is always yes, always. So according to Moscow's theorem, it's already too late for that reason too. So for those two reasons, we don't even have to get into the quantum timeline with those kinds of customers. They just need to understand that and then start acting accordingly.
Konstantinos, could you add in? There's this phrase that I think some of the users might recognize. It's called "store now, decrypt later." And I think that had to do with the latter part of what you were saying. Maybe you could delve on that just a little bit more, because
sure,
you described part of it, but I don't know if the narrative is strong enough for people really to understand what that means.
Yeah, it's sort of covered inside of Moscow's theorem, right? When I say how many years does something have to remain secret, of course, you can capture packets now. And we know nation states are doing this, of course. They've been doing it forever. And why have they been doing it forever? Not just quantum. They're also doing it because of the risk of side channel attacks. We see side channel attacks come up in all types of cryptography. So we know China's capturing our packets. I'm sure the US is capturing Middle East packets. It's just a thing that goes on, and you hope. So you store that now, you hang on to it, and then the hope is that one day you can reverse that using a quantum computer, let's say, and that some of the information is still relevant. That's why that length that a secret needs to be kept comes into play. With credit card data, who cares, right? If you decrypt a credit card transaction in 7 years, whatever. The number will change, all the information will be invalid, the code, whatever. But some of these secrets with that long shelf life we discussed, you can capture them now and decrypt later. And of course, in the case of reversing keys on a blockchain where, address reuse isn't being monitored, you have a serious problem. There was recent studies done of Bitcoin and Ethereum, and there was a scary number of addresses that just remain the same. And as a result, like there's a good 60% of addresses in aggregate that can just be, you could just download the blockchain and start reversing private keys. They just haven't changed. And then when they can be changed, that introduces all sorts of other problems like faster than attacks with malicious nodes and capturing packets. But yeah, of course, you don't have to worry about people capturing your data when a quantum computer is live. They can capture it now and do something with it later on. So like I said, it's already too late in some ways, but the best we can do is just move forward.
We've talked about in the past a couple of times, the immutability of blockchain being one of the advantages, right? In that it allows everyone to verify their own transactions and be able to read it for themselves and see how it went. But at the same time, that immutability poses this threat, because if you are using the asymmetric private public key encryption, which came out in the 1970s, then that poses a problem. So please, I interrupted. Please continue.
Yeah, no, that's absolutely true. This stuff's going to be around for a very long time, and then change is slow, right? I mean, the reason you guys created a whole new project, I'm assuming, is because you couldn't just go to Ethereum and be like, I think starting tomorrow we should have post-quantum cryptography in place for everyone. Let's go. And no way. You see how long it takes to do things like move to, sharding, proof of stake. Like these types of things take time to implement. And it's going to be the same with post-quantum cryptography, of course.
I've
Yeah.
heard it's compared to Y2K in
Yes.
some ways, and we call it on the team, we call it Y2Q.
Yeah, we do the same.
How? Oh, okay.
Yeah.
However, I don't think this is not the same thing, because you can. It seems like there was a lot of hype around Y2K. Everybody knew of it, knew about it, but the only quantum in as a household name is mostly nowadays due to Marvel action movies.
Yeah.
Right, nobody's really talking about this. And I've worked in CISO departments and security departments for Fortune 500 companies, and I remember walking around like a year ago and just as an experiment, kind of talking to people, hey, what do you think about this quantum thing? And literally it's like, what, Ant-Man? And these are tenured professionals. So the way that this evolves is the way that it appears that it's evolving with the data that exists. A lot of great great points that you brought up, that I share the similar opinion on. I don't know how this ends. I don't know how it goes, but I don't think it's the same as Y2K, because everyone knew about Y2K. It was all over the news, and people knew where the risks were, like in time. Like they knew that code needed to be touched, and it was their own code. With this, this is different. You're relying on, let's say you're talking about building in maybe an IPsec point-to-point tunnel, on phase 1, phase 2, and then you're encrypting it that way. A lot of this depends on manufacturers that are outside of your control, not code that you've developed inside. And I don't see a lot of them talking about it either. I see a lot of business being driven around. I almost hate using the word AI, but I see them doing SecOps around AI. In other words, machine learning, as far as being able to mitigate attacks and different attacks in real time. So eventually you have AI on one side and AI on the other, attacking each other, and both evolving at the same time faster than a human, a SecOps human could. I see that, but nobody's talking about this.
Yeah,
we are. Yeah, but
yeah, there's a few things that have to be done, like you kind of indicated there. You do have to worry about this large landscape, right? When you start to address this problem. Y2K, of course, was like an infrastructure thing. We knew it was coming. It wasn't really considered a security threat. It was just considered more like a mass denial of everything. Like just nothing would run anymore. It wasn't really considered security though. I like to think of it as like a blend of Y2K and like Heartbleed. Like Heartbleed attacked everybody's.
It's like
pretty much.
Yeah,
It was, and we didn't know it was coming, and it was right there in front of us. We just didn't know. So this is the first time I like to say that we have a 0 day that we know is coming. Like we've never had that before, right? This is it. This is the first 0 day that we have to come up with a new word for it, because we know it's coming. So Y2Q is kind of a fun way to blend things like a mass event like Heartbleed, but also that we have the deadline that's approaching.
Yeah.
So I like to remind folks about that. And there's a lot that has to be done. Think of like third parties when we're talking to companies about. It's really about becoming crypto agile. So we go in and we call it like a post quantum crypto agility assessment. Like how agile are you? Are you ready to implement the new ciphers? And there are a few sticking points there. It's like, are you hard coding cryptography everywhere? That's a problem. Are you relying on third parties who have no path towards post quantum readiness? That's a problem, because they might be handling a whole bunch of your infrastructure. So it's like looking at all these things, and then also, of course, doing like a technical audit of what cryptography you have in place. You might not even realize you're using stuff that's vulnerable now. Forget about when quantum comes around. Identifying all these pain points, and then coming up with recommendations, and then further rolling out something that will be ready to handle post-quantum cryptography when it arrives. So it's a big process, and it's a big job. And the thing is, literally everyone has to go through it. Everyone's going to have to do it.
Yeah, you kind of answered what my next question was going to be in terms of like first steps people can take, whether it be people, institutions, big companies, fill in the blank. If I were to relate it to like an analogy of, let's say, you go to the doctor for your annual checkup, and your doctor tells you, hey, you've been slacking for a little while, your cholesterol's high, something else is here, but like you're not so far gone, but it's definitely a problem that if you don't address, maybe that's not the completely applicable analogy, but if that's, say, the situation, that person is that organization that's steering a big ship, or it's just an individual, what are some additional things that people, institutions, organizations can be doing within this next year, taking, right now, to additionally, set themselves up? Or maybe they're not even in the position where they can necessarily make change themselves because, big organizations, they have legacy solutions, a lot of stuff that they're working with. What are maybe some, good starting points for at least them to open up that conversation within their, let's say someone within a big organization is watching this, or an individual is like, hey, what should I do? Shoot, I know I might have not done anything so far, but is there anything else that you would recommend as some other best first steps? And it's going to be unique to everyone, but
Yeah,
in generally speaking.
there are a few initial things you do right away. One
Yeah.
is like being aware of the problem, right? So few
Yeah.
companies are fully aware, making everyone sort of aware that the quantum threat exists, that it's real,
Yeah.
that it's going to be everybody's problem soon. That needs to be established throughout leadership, or else you're not going to have the
The
buy-in that you
buy-in.
need to
Yeah.
get anything done. You're going to have to pick people in your organization who want to be responsible for this. It is a great way to also stand out. Like, let's say you're a security professional, you don't need to go and study anything quantum to make this your
Yeah.
specialty, right? Because this
Yeah.
quantum's just the threat here.
Yeah, you're
Um,
bringing it to the table, and showing, hey, this. We should pay
yeah,
attention to this and help spearhead that.
yeah.
Yeah.
So you're the one who's like become the champion. You're taking this on,
Yep.
but you don't have to understand superposition or entanglement or or anything how to program in
Yeah.
Qiskit. You don't need to know any of that stuff. You just have to understand it's the threat. Just like when you remediate Heartbleed, you don't really have to understand how to write the exploit. You just have to know that you have to patch these servers. So that's great. It's a great way to stand out as a professional, to show that you're thinking of only post-quantum safe cryptography going forward, and agility, and that becomes your new mantra. And companies sometimes, even though they're slow, they do like to be part of like a wave, right? Like if you remember when agile development became a thing, everyone was like, hey, are we doing agile development? We need to be doing it too. Oh my God, everyone's doing this. And I think the same kind of thing might happen if we're lucky over the next year with this crypto agility idea. It's like, oh wait, are we crypto agile? Are we coding this way where we're not going to have to rewrite everything because rewriting everything costs money? And if you can make those arguments internally, you get the buy-in. Then there's some other simple stuff you could do. Like if you know it'll take a long time to migrate a bunch of legacy systems and things, this might be your reason to finally go to the cloud. And the reason I say that is AWS has been using hybrid post-quantum safe infrastructure for quite a while now. When they first tried to set it up, it wasn't that great, so they didn't roll it out. But now it's rolled out and available. What they do is they basically have the standard ECDSA tunnel, and it's wrapped with one of the finalists. So Crystal's Kyber or Bike, for example, they'll be wrapping it, and that way the hope is that if those packets are captured in the future, the quantum computer will be stumped by Crystal's Kyber and will never be able to actually see the ECDSA. So that's like one approach. So it's a good argument for companies that have been hesitant about going to the cloud. That ironically, when they used to worry about security and all this going to the cloud, it might be the more secure route going
Yeah.
forward, because at least it's in place with AWS, and Microsoft has followed suit. Um,
Yeah.
and any of those transmissions, I mean, anything web-based was always sort of able to be post-quantum safe. Browsers in their nature were always like upgradable. We started with SSL 1, 2, 3, TLS 1, 1.1, 1.2. Like it's just what happens. Cipher suites get updated. So that kind of infrastructure is a good one to rely on. So these are good arguments you can make that don't really cost. They cost money, but they don't really cost more money. Like moving to the cloud, it's a juggling game that you have to do for your organization anyway. And people might find it's better than like trying to maintain this legacy hardware. So once people think of it that way, it becomes a little less ominous a problem, and it becomes a good excuse to like take some of these proactive steps. So those are some like the basic things you could do. But yeah, I mean, it is a lot of work, and I do recommend having someone who understands this stuff really audit what cryptography is in place, and how data is in motion, and what your crown jewels are. Everyone forgets crown jewels.
Yeah.
Because once you identify your crown jewels and how they're being protected or not, you can make those first phase 2 steps, what I like to call phase 2. That's where you do like maybe a pilot program. You can use something like post quantum hybrid solution to protect really critical transmissions or whatever the case may be for your organization. And that's like a sort of stopgap measure until you're ready to roll out everything, key management, the whole bit from scratch going forward. But I wouldn't recommend anyone spend money now on rolling out anything cryptographic without considering post quantum. That's a really bad idea because within a year you might have to rip the whole thing apart.
Yeah, and if you don't have to do it in a year, it's just it's inevitable that it's gonna happen. So if you're gonna be putting time, resources, bandwidth towards that, might as well put it towards something that will be able to stand, test of time in terms of the durability of it. If your aim is security, don't do the the easy solution for that. But no, that really helps answer my question, and that the way you explain that too also is in a leveled up way where it's not just 0 to 1. There's, as you mentioned, hey, phase 1, phase 2, there's a lot of ways to go about it, and the way you explained it makes a lot of sense in terms of the, hey, this is a good way to be looking at it in a way that's approachable. So no, I appreciate that. I think Michael, I think it would be good if we chatted with Konstantinos for a few in terms of, there's been a lot of recent news on quantum computing. I think one of the issues I always have with just news in general around the quantum computing space is the classic idea of news articles is there's a lot of clickbaity headlines, but underneath that there is a lot of important things that are happening, but it's hard to unpack it sometimes. Konstantinos, could you maybe fill us in a little bit in terms of maybe some of the recent quantum computing news, whether it be China, rest of the world, and maybe tying that, obviously there might be some geopolitical impacts there. Could we touch a little bit based on some of the recent stuff? I know that it changes every few months, but I think it's important to at least kind of maybe from a macro level cover the landscape and what we're looking at, because it does play an impact and a role.
Yeah, there are a few things that are going to impact the timeline. One of them, maybe not so much. I'm assuming you're talking about the December 23rd paper about factoring numbers that was done with Chinese researchers. That built on the work from, I don't know if you remember back in 2021, there was a paper by Schnorr, not to be confused with Shore. And in it, it caused a big ruckus. Everyone thought, oh no, we can factor numbers, but no demonstration was made. No actual speed up was proven. He actually withdrew the paper, resubmitted it with some tweaks, which kind of quieted everyone down, but didn't really make a statement either, in my opinion. So that work was sort of like the basis for this more recent work. And what they did was they used a quantum approximation algorithm, or QAOA, and they ran that on a real quantum computer. So if I recall, it was they used real 10 qubits to factor something like, I think it was a 42, 48-bit number, something like that. I think it was 48-bit. And
48.
Yeah, it was 48. And they were able to show that, and they were able to show how many depths of circuits it would take. But then they did something a little dangerous. Okay, so they did that, great. But then they extrapolated. They said, cool, so 10 qubits, you get 48 bit. So we think it'll take 372 qubits with 1100 circuit depth to do RSA 2048. That is a really big leap to make. I mean, the orders of magnitude of assumptions that are being made there, it's hard to even characterize. It's sort of like taking a bowl of water, spinning it, and saying, oh, you see this motion here? I think I just figured out how the Milky Way galaxy moves. Wow. Like, it's literally that many orders of magnitude.
Yeah. No pun intended. It's a quantum leap from one to the other.
Which is funny because quantum leap is, of course, the smallest distance that anything can move in energy level. So whenever I hear quantum leap, I cringe because that means literally the smallest energy increase you can measure. That's a quantum leap. So I don't know why people view that. Anyway, it's funny for me. But so it's not safe to then assume that 372 qubits would be able to do this. And the reason is we've never seen a QAOA speed up. We haven't. It's just never been done. And because of that, and this huge leap, and then one other factor everyone forgets, the best we could do right now are the 4 nines of engineering, 99.9% gate fidelity. This extrapolation will require 5 nines, so 99.999. We don't really have that. So to expect 1100 gates to achieve 99.999% fidelity to give you an answer is a tall order. So qubit count wise, it sounds like we have it, but we really don't, because sure, IBM has 433, but we don't have the ability to run that many gates with that little fidelity anyway to test their theory to see if it's true. When we get that, we might still not find that it's true. We might still find that the speed up isn't there, and it could take 1,000,000 years anyway. So we just don't know. So there's a few major assumptions being made there. But what's exciting is maybe something in that paper could be a kernel for advancement going forward. Maybe some new approach, some refinement, or some multi-stage process will be impacted by this. That we also don't know. So I don't want to just throw it out completely as hype, but I just know that based on what's there, it doesn't really prove anything. And they kind of admit that too. Before it gets to the tremendous appendix, there's even a quote there, something to the effect of that, because of the nature of QAOA, they kind of admit it. So it doesn't really mean that next year we're going to be cracking encryption with these machines, but who knows? It might lead to something useful. Now, it might be worth following up some other things that are going on that aren't making enough headlines and should. Whenever I remember I referenced to folks that the old cryptographers that'll get up there and say 30 years away. If you ask them after what interconnect is, they'll just look at you and go, what? Because whenever they talk about quantum timelines, they talk about developing error-corrected qubits on one machine to scale. And yeah, that's really hard. But what they're forgetting is that quantum doesn't really work the way classical does. In classical computing, you can connect a bunch of computers using a grid scheme. In some ways, you could say that anything going on a blockchain is some kind of bizarre grid, right? But you're not really getting 100% of each machine. You're not even getting 10% of each machine, honestly, when you do grid computing. The overhead is tremendous. Like the SETI search years ago, your home computer would use a little percentage to contribute. It wasn't really contributing that much. With quantum, you can actually connect these machines together because of entanglement, and the qubits don't really care where they live. So if you build a perfect 1,000 qubit machine, so error corrected, that means it's technically going to have more qubits depending on the architecture. It could have 10 times as many, 1,000 times as many, whatever it is. But those qubits are doing the error correction, and then you end up with these logical qubits. Once you have, let's say, 1,000 logical qubits in a machine, error corrected, perfect, running, and you build another one of those, and another, and another, and you connect them with Interconnect, you do have a machine that can crack RSA. So even though you hit 1,000 qubits, you're like, oh, we're years away. No, you're not. You're just duplicates away. And that's something everyone forgets about. Interconnect is like the like unknown secret that's not really being hidden from anybody. It's just no one's taking the time to look into it. At first, Interconnect is going to require the same type of machine. So it'll be used to chain together transmon only to transmon only, or trapped ion to trapped ion, whatever the case may be. But this is actually the building block for some companies going forward, like PsiQuantum. When they say they're building 1,000,000 qubits, they're not really going to build a 1,000,000 qubit board of any type. They've admitted they're going to have modules in there. They're trying to find the optimal number of qubits per module, and then they're going to have them interconnected to make this perceived 1,000,000 qubit machine. That's the only sane approach. We don't know what that number is depending on technology, but we do have a feeling that it exists per technology, because the more qubits you cram in, the more control hardware you cram in, the more sending of signals, the more like the noise just increases. It's just going to happen. So there is some optimal number. We just don't know what it is yet to make those modules. I think it's going to be pretty small, honestly, but it doesn't matter if Interconnect is working correctly. And yeah, this of course leaves out any other surprises, like Microsoft proved their topological gap for Majorana fermions. Majorana fermions, if those could be turned into qubits, would be mostly error-free. So if you had 1,000 qubit machine made of those, it would be like 998, error-free qubits, pretty much. So that would be insanely cool, but there's a lot of technological hurdles to making that into a qubit. So these surprises will come up also, but Interconnect is that one big timeline shifter that everyone ignores, which is why I think it is possible by the end of this decade, we could be seeing a real threat to definitely blockchain and potentially RSA.
So with Interconnect, so this is interesting. I actually haven't heard of that before. But it sounds like if I were to, based on an analogy of what I remember the set actually was in the SETI project. I have a certificate everywhere, somewhere stored from like 20 years ago or the 90s. In that case, you had CPUs, isolated CPUs that were all feeding into the cloud. But in your scenario, the Q CPUs are all entangled with each other. In other words, it's one CPU that, let's just say it's factoring, and then you have decoherence. They would have to be put back into entanglement classically, I believe, because they have to in causality, they have to be brought back together in some way or another.
Yeah.
Sublight speed, but then you can start it all over again. But we already have the internet, so if I'm not, and if I think of an analogy, this is a lot like, let's say there is some sort of astrophysics event, and you have all telescopes in the world pointing at this one thing, trying to understand this one thing, and they're working together. That might be an analogy, but I can't think of a real good analogy to explain that the CPU itself, which is typically, an inch and a half in a ZIF socket, actually extends across the world. It's working as one actual processor rather than symmetric multiprocessing. It's more linear, but not linear, more superpositioned linear. But maybe you can comment on that a little bit.
Yeah.
It was the first time I've heard about interconnect. So
yeah, there's a few things we've never experienced before when it comes to quantum, right? One is just the nature of a qubit. When you're talking about classical CPUs, let's say you have a gigahertz CPU, and then you get a 1.1 gigahertz CPU, you can expect a 10% increase in performance. It's easy to imagine. You see the math. It's simple. But with a qubit, if it's a perfect qubit, perfectly entangled, error-free, anytime you add a qubit to a system, you just doubled its power. You doubled its ability to address states of information. So we've never experienced anything like that. Like when you hear of the IBM 433 qubit machine, if it was a perfect qubit in that machine, and then they announced a 434 qubit machine, people will be like, big deal. But in actuality, it's double the power. so that alone is something that's hard to wrap your mind around. Now imagine adding these machines together. You're way exponentially increasing the power when you do that, because you're adding hundreds, thousands of qubits at a time, and it's just mind-blowing. And they are acting as one with very little overhead. Once we get interconnect right, the machines that they're experimenting with now are very small, but that will change. There's a company, Entangled Networks, doing some cool stuff with this, where they're showing like the ability to prove that 2 optimal 6 qubit machines with interconnect would actually behave better than a 12 qubit machine, just because it would be, maybe they were more optimal than the 12 qubit. So we're already seeing these initial proofs that interconnect might be the way to go. So yeah, it's just hard to wrap your mind around, because that's how it is. When a qubit is perfect, it's 2 to the n for the qubits. So you can see how things get out of hand really quickly. And to have a perfect machine with a few hundred qubits, if you wanted to simulate that with classical computing, you'd have to convert the entire known universe to a machine, which you couldn't do. And you still wouldn't have enough ability. There's only like 10 to the 90 particles in the known universe. You just wouldn't be able to address all those states, all those bits, with that kind of power. So yeah, these are things that are being ignored when we talk about the quantum timeline. And of course, the other example when it comes to blockchain is we don't even need the machine. We just need to be close to having the machine. If I came on this podcast today and said, oh, I think we already have the machine that can, destroy Bitcoin, what would its value be tomorrow? Elon Musk has proven that just when he says that he doesn't want to accept it because it's bad
just
for the environment. A tweet, it'll drop in value. It gets even more dangerous when people start to understand the quantum threat, and when people speculate that maybe China has a machine that can like steal your wallets from, your keys.
Yeah. As a closeout question, I think it would be good to just touch on, wrapping up. I think it would be just, open-ended question. What are maybe one thing or a couple of things? I know you've mentioned a few already that you're excited about, at least the future of what's being built in the quantum computing space. What else are you kind of, what are you reading? What are you digesting? What are you excited about? Whether it be from conversations that you've had with guests on your podcast, or just in the, industry as a whole. What are you really excited about this next, whether it's 6 months, 12 months, 18 months away? What are you excited about at the present moment moving forward? Maybe an interesting resource for people in the community viewing this to watch, or just in, broadly speaking?
Yeah, this is going to be a really exciting year. Even though we're sort of in this like mini quantum winter already, just because potential threats of recession. Some companies are like, maybe we should wait. But there's a lot of exciting things happening. This year, we're going to pass the 1,000 qubit mark. That's pretty exciting, right? Even though they're not perfect qubits, it's still a huge number. It cannot be simulated with a classical computer. So we're bound to start to see even some poorly written algorithms that will show true benefit or advantage, as we like to call it, because just the sheer horsepower that's available. We're also seeing refinements and optimization processes that are starting to show advantage or an edge. I published a paper where we did financial index tracking. We were able to outperform, let's say, the S&P 500 with a tenth as many stocks, just because of the optimization power there. So those initial use cases are starting to bear fruit. And as the machines get more powerful, this will be the year of some machine learning advantage, I think. Things like binary classification. I think you're going to find that quantum computers are going to be really, really good at selecting good from bad with things like SVMs. You'll have like this big data set. He's a good credit risk, a bad credit risk, whatever. Like you'll be able to divide that data with a little more granularity with quantum computers this year, I think. So those are some of the biggest advances that I see coming, those general use cases. And the other one, which is exciting, is we've learned so much from quantum that we can start taking advantage of classical hardware better. There's this whole idea people will consider of quantum inspired algorithms. So it's where you take really powerful, limitless classical resources like the cloud or whatever, and you apply these new algorithm approaches to it, and then you use that horsepower to get better results. So this is a great way for companies to onboard quantum into their teams. Like you can learn the quantum inspired approach. We do this for customers. You learn a quantum inspired approach. You run some kind of project, and then you get better results on classical hardware. And then when quantum computers catch up, you're now going to be orders of magnitude ahead in performance because you already learned what was required. So that's kind of an exciting onboarding thing where it's not just a toy, like a toy project. You can actually turn around to your, higher ups and say, look, we're saving 20% here, or we're actually making money if it's a financial application. So these are exciting things coming.
Yeah, you brought up a number of great use cases there that kind of fit a lot of that there. I think kind of as a closeout to today's episode, first off, myself and Michael really have enjoyed this conversation. But as a closeout, our audience is very, very niche, very focused kind of at the intersection of quantum and crypto. For those that are watching this, whether it be, individuals that are just interested in making sure that their digital assets are staying post-quantum secure, or whether it's people within big organizations, institutional money, et cetera, where's the best place or two that those that are watching this and want to learn either more about your work, or if they want to maybe listen to your podcast, The Post Quantum World, where's the best place or two that they can find you and, just learn more, or maybe even strike up conversation with you, maybe if it's at a more, company, larger level?
Yeah. So the Post Quantum World is available wherever you get podcasts. We have like a vanity URL for it, I think. So you just go to
Yep,
protiviti.com.
I'll link it in the show notes.
Yeah. You can just go to that vanity URL too to get to it quicker. And we work with companies for both sides. So the post quantum cryptography and also use cases, actually doing something with these machines. On the crypto side, I think it's important to pay attention if you want to introduce it into your organization, that if you're going to build something internally, you pick something that has a post-quantum path forward, So let's say you wanted to build some kind of internal blockchain application. I would recommend looking at something like, I don't know, R3 Corda, or something that actually has the switches already enabled moving forward. You don't want to be locked into something that's potentially, sketchy in that way and a problem. If you want to invest money in crypto, I can't give investment advice, but it would be interesting to see, how, QRL, for example, grows, just because we know that it's not going to face that problem going forward. So I'd be a little nervous for the time being, investing too much money in Bitcoin or Ethereum. Forget about the volatility. They're just not there yet. It is a potential like disaster waiting to happen.
Yeah, no, I think I really appreciate it. And Michael, anything else to add? I think on my side, more than anything, just really enjoyed this conversation. I think it, just as we overlap on the intersection of quantum and crypto, you really kind of pull together and overlap with that, but where it can be applicable on, the business impacts for, institutions, corporations, down to the individual level. So myself and Michael, we really, appreciate the conversation, and we look forward to chat soon.
Yeah, this is great.
Thank you.
I really appreciate seeing you again. One day you'll end back up on mine again, and we'll see what happens.
Sounds good. See you, Konstantinos. Bye-bye.
Okay, thanks.
Thank you.
Bye.